All right, welcome to your AP Unit 1 pre-lecture on the moles and mass percent. The mole is a super important goodness gracious, unit and concept that I introduced early on when talking about scientific notation in that pre-unit at the beginning of the semester or the beginning of this course. And now we're going to start really looking into it in terms of how we can use the mole as a mathematical concept to describe, predict, quantify, and identify particles, compounds, and eventually reactants at the larger scale. Okay. So first and foremost, we have to remind ourselves how we measure particles. So don't forget that particles are considered mass, okay? And we consider mass as the amount of matter. And so we have a law that kind of goes with this, is that it's called the law of constant composition, that all samples of a given compound have the same mass or amount of matter ratio of constituent elements or elements that are used to form it, right? Constituent elements. So I think I introduced this earlier by chance, and I may not have said it, the law like this, but we say that, right, H2O will always have a ratio of 2 H's and 1 O. Its constituent elements of hydrogen and oxygen will have a consistent or constant composition ratio in order for that compound to still be that compound, right? Sounds silly that we have to give it a law, but scientists, we make it concrete, right? We put it in writing, we stamp it on our foreheads, and we share it with everybody. So the mole is a way that we quantify this ratio at a large scale, at a macroscopic scale that we can actually, one, measure in lab and talk about and observe, right? So the symbol of the mole is MOL. Now, if you're thinking to yourself, that is one letter different than the word the mole, you are absolutely correct. I do not know why we felt the need to abbreviate it. And we call the mole a number counter, okay? A number counter. And the big idea behind the mole is okay? It is essentially a multiple, a macroscopic, okay, way, or a macroscopic scale up, okay? We're scaling up how we count, a macroscopic scale up that allows us to quantify at a large / observable scale. Okay. And I know I use kind of scale twice, but the idea is that, like, we don't, when we talk about atoms and particles in every day, we don't like say to ourselves, ooh, can you give me a glass of one particle of water? You know what? Actually, I'm feeling really thirsty. Could you give me a glass of 3 particle waters, just like really to quench my thirst? We say, can you get me 6 ounces of water? Or can you get me a jug of water? Do you know how many water particles in that? So many. We couldn't count them if we started looking at an individual amount. But if we can use a number counter, a unit that represents a large scale, a unit that represents a large sum, we can scale up our terminology and in a way that allows us to, one, interact at the human level, right? The human scale. So we've introduced this before. The mole, the number counter, represents Avogadro's number of 6.022 times 10 to the 23rd. We say things, anything. We can have an Avogadro number or a mole of anything. So you can kind of compare it, by the way, to like how we treat the word a dozen, right? A dozen represents 12 things, okay? So we like to say, instead of saying, hey, I have like 6.022 times 10 to 23rd atoms in that thing, I have a mole of atoms. Oh, and instead of saying I have 12 dozen, or sorry, instead of saying I have 12 donuts, I have a dozen donuts, right? It just kind of removes, okay, this level of extraneous speech of dealing with larger numbers when we could just say, oh, I have 3 moles. What would 3 moles be? Well, it'd be 3 times 6.022 times 10 to the 23rd things. And for us, the things tend to be atoms or particles. So we like the mole because it allows us to also talk about characteristics of an atom, okay, or a compound at a larger scales, such as molar mass. So when we look at the periodic table, what we usually see is atomic mass, right? The mass of one atom, the mass of one compound particle. But again, we don't work with one of anything really. So what we say is, well, if I multiply, if I were to take 6.022 times 10 to the 23rd atoms, okay, of an element, such as like, let's do carbon. Okay, if I were to have 6 point, hold on, let me change my thing. If I were to take one carbon atom, I would have an average atomic mass of 12 AMU for one atom. Okay, one elemental atom. But then if I were to use the mole and I were to scale up by 6 point, okay, 022 times 10 to the 23rd, okay, what I would find is that if I were to put 6.022 times 10 to the 23rd atoms of carbon in a container, I would see that my mass, one, scales up to a measurable amount, and specifically it scales up to be 12.01 grams for, okay, for 1 mole of that, I get 12.01 grams of carbon. So carbon has a mole mass, a mass due to there being a mole of it, of 12.01 grams per mole of carbon atoms. And so what we're seeing is a really handy dandy conversion. Okay, we're seeing that we can look at the periodic table, take the atomic mass units, and simply apply the mole and turn it now into a comparable, okay, equivalent mass, just flipping the units from AMU to grams. And that's really nice because that doesn't really take it much math, right? We just basically change the units because AMU is one atom or one particle's worth of mass. And when we multiply it by the scale of Avogadro's number or the scale of a mole, we end up now being able to put the equivalent value just in a different unit of grams, which is awesome. So how about a compound? What we do for a compound, let's say CO2. What about CO2? Well, CO2 would have a particle, single particle mass of 12.01 AMU, average atomic mass, plus 2 oxygens, 2 times 16. And I would get, okay, a mass of about 44, okay, 0.01 AMU for a particle, one particle of carbon dioxide. Now, if I want to scale that up, because I'm not going to breathe in or breathe out actually one particle of carbon dioxide, I breathe out many particles. And so what I say is, well, times 6.022 times 10 to the 23rd, if I were to scale up by Avogadro's number or the mole, right? Notice this is now a unit conversion. These are equivalents, okay? I would get that my molar mass for that compound, my mass for a mole of those compounds, 6.022 times 10 to the 23 of those, is going to be 44.01 grams per mole of CO2. So go ahead and try the next ones on your own. Okay, so hopefully you guys paused me and these are the values you got. If you weren't really sure how I did water, I just simply summed up the total mass of each constituent element's atom contributed, and then I scaled up by the mole, okay? So notice now, we've been introduced actually to 2 new equivalents, okay? 2 new unit conversion factors. We got introduced to the mole and Avogadro's number being a conversion factor because they are essentially the same thing, just a different unit, equal meaning different units. But we're now actually seeing that our molar mass is a derived unit. And a derived unit means it has 2 or more units to make up 1 unit. And so that means we actually now can turn our value, our characteristic into a math tool, which is we can turn molar mass now into a conversion that we can use to go between grams and moles for a particular substance, right? So what we're going to do is I'm going to show you how to start doing unit conversions now with the molar mass, which is actually the real value of the molar mass, is that it allows us to convert, okay, between these 2 units of grams and moles. Grams is used at the laboratory level, but moles is used at the conceptual level, okay? And both are really important for chemists. So let's say I have how many molecules are there in 65-gram sample of Na2HPO4, sodium biphosphate, okay? So what we would say is, well, always start when we're looking at a unit conversion problem, always start with what you're given. And so you're given that I'm starting with 65 grams of Na2HPO4. Now, if I'm going to draw a little map of where I want to head, I want to go from 65 grams to molecules or things, okay? Or things. So I need to get from grams to molecules. Now, I don't have a conversion that allows me between what I just introduced. I don't have a conversion that it directly relates grams to molecules. But I do know that if I use molar mass, I can go from grams to moles. And if I get into moles, I can go from moles to things, Avogadro's numbers, things or molecules, right? Things being molecules in this case. So what I'm going to do is I'm actually going to set up a two-step conversion. So first and foremost, I'm going to use, okay, molar mass of Na2HPO4. So the molar mass of Na2HPO4, I'm going to do capital MM for molar mass, is going to be about 141.96 grams per mole. Okay. Now, that's how you would write molar mass. It has to be grams over moles. But I'm going to turn that value into a math tool. So what I need to look at is, okay, now I'm going to look at that more as a math tool and more as an equivalence factor. So the question is, how am I going to cancel out my grams to get into moles? I'm going to have to flip the ratio. And I'm going to say, well, for every 1 mole, I know that I have 141.96 grams of Na2HPO4. Okay, I've turned my molar mass number into a math tool in order to create a relationship between the two units I want, grams and moles. Okay, and I've ordered it in a way that my grams cancel, and I'm just left with moles of Na2HPO4. Okay, using the molar mass. But that's not where I want to end, because what that's going to get me to is all right, hold on. That's going to get me to some value in moles of Na2HPO4. But I want to be in grams. So what I'm going to do is now next step, I'm going to say to myself, well, now that I'm in moles, because this is kind of what I'm left with initially, left in moles of Na2HPO4 after I would have done that math. I need to figure out how to go from moles to molecules. Well, I know, okay, I have a relationship between amount of things and a mole, Avogadro's number. So I'm going to use that standard relationship, that equivalence factor, to carry me, okay, to the next stage of transformation, or the next unit conversion. And that is going to be, I know, well, for every 1 mole, I have 6.022 times 10 to the 23rd things or molecules, okay? And so what's going to happen is, let me move this, make it smaller. Okay, what's going to happen is now when I partner it with a second unit conversion, a successive unit conversion right afterwards, I see my moles cancel out, and all I'm left with is, okay, I forgot to write molecules. All I'm left with is molecules of Na2HPO4. And don't forget, whenever we write a number initially, the given, we kind of assume there's an invisible 1 underneath. And then what I have is now I have this mathematical process that reflects a conceptual transition between various units using equivalences or connections, standardized relationship between the various units. And so what I would do is I would simply now multiply. I would say, okay, I have finally got myself in a mathematical setup that leaves me with just molecules of this compound, which is the units I want. So now I'm going to now solve for the value, the actual numerical value. And I'm going to do 65, all the top things to multiply together. 65 times 1 times 6.022 times 10 to the 23rd. Divided by, put a parentheses, 1 times 141.96 times 1, end of parentheses. And I get that in 65-gram sample of Na2HPO4, I would have approximately, okay, 2.8 times 10 to the 23, 2 sig figs, the 23 molecules of Na2HPO4. All right. And that right there is how you would do dimensional analysis with the mole, or a multi-step unit conversion with the mole. I realize some of you guys might be a little confused how I got the molar mass with sodium biphosphate. Remember, you take the sum of the mass of each atom in the compound. So I had 2 sodiums plus 1 hydrogen plus 1 phosphate plus 3 oxygens. Okay, so sorry, there's a drum line happening. It's pep rally in 2023. So why don't you go ahead and try the next one on your own and follow my example above. Okay, so hopefully you got the following setup. Our map of kind of where we want to go. We want to go from 87 grams of sodium sulfite to molecules of sodium sulfite, Na2SO3. We set up our starting with our given, what we know, and then we say, okay, to go from grams to molecules, okay, I can't quite do that in one jump, but I can stair step it. I can do it in 2 jumps. I can get from grams to moles using the molar mass, turning the molar mass into a math tool and flipping it accordingly so that my units cancel. And then I can go from 9 new units of moles of sodium sulfite to molecules using Avogadro's number and the relationship with the mole, the equivalence factor of Avogadro's number. And I cancel out moles and I'm left in molecules of Na2SO3, and then I do my math. I perform it, realizing that the first number is like saying over 1, and I multiply all the numbers on top of the fractions divided by all the numbers on bottom multiplied together, and I get a value of 4.2 times 10 to the 23rd molecules of Na2SO3 to the 2 sig figs. So we actually have a unique name for this type of dimensional analysis with the mole, and that is stoichiometry. So you could just think of it as your advanced unit conversions with the mole, okay, used to quantify chemical species in a reaction typically. So we kind of have this little 3-part floral diagram. If this helps you, awesome. If it doesn't, no worries. If you want to make it more linear, do what you need to do, but this is just a suggestion. I thought it was really pretty. I like the font. But what we see is that we can use, and notice they did kind of cut Avogadro's number a little short. We're going to use 6.022 times 10 to the 23rd. It's just a little bit more precise and more accepted by the AP. But what we see is that you have a diagram of how surrounding the moles, how we go from particles to grams to liters and so forth. Tomorrow, we're going to have you talk about this transition from moles to liters, with particularly focusing on gas-related species or chemical compounds that are in the gas form. All right, but that's tomorrow's thing. Today, we mainly focused on the particles, okay, to grams kind of relationship via the mole, through the mole. So how can we use, by the way, this concept of the mole to kind of go back to the law of constant composition and quantify our ratio or a constituent element ratios in a compound? So what we can look at here is that what we see is in water, for example, when we say that our constituent ratio of our constant ratio of the constituent elements in water are going to be 2 to 1. Well, if we have a mole of water, if we were to scale that up to go from talking about it from an single atom view to a mole view, we would say then that we have 2 moles of hydrogens for every 1 mole of oxygen to produce a single mole of H2O compound. Okay, and so what we can do is we can use the mole to quantify at a macroscopic level, the ratios necessary in a compound. So let's look at this. How many moles? Why do we say models? How many moles? Gee willikers, spell check. Of hydrogen are in 3 moles of H2O. So if I know that, okay, for every, I start with my given 3 moles of H2O, I know that for every 1 mole of H2O, I have a ratio of 1 to 1, right? I have a ratio of 1 to 1. So for every 1 mole of water, I'm going to have in my constituent elements 1 mole of oxygen. So I set up my unit conversion and I cancel out my units of moles of water and I'm left in moles of oxygen, my standard relationship, my equivalence factor, and I get that according to the law of constant composition and the concept of the mole, in 3 moles of water, I would have 3 moles of oxygen atoms. And that's kind of how we start using that. We're going to look into actually calculating empirical formulas of unknowns based on measured mass values in lab and using the mole concept to create definite ratios. But that will be a lot of tomorrow and the next couple days. So, and also fun fact for 2023 people, we have a previous student that has volunteered to teach this with my guidance. So I'm really excited to have him be on video and offering you guys a little input. Otherwise, for other years, it might just be me. So I don't know, but have a great one, guys. Good job.